Are we ready to start? Well, let's remember what happened last week. So last week we talked about the smash product on the internal Hom for the category for the homotypic category of spectra. Now the smash product is more or less clear. At least it's clear exactly what we need to check to have the properties which we want the product to have. As for the Hom functor, we had two definitions. And the first one didn't work, and I still don't have a construction which would work on the level of spectra, but if we if we're only interested in the homotypic category, then we can use the second definition, which proceeds by saying that this functor, the left-hand side as a functor of x, is representable. And I haven't forgotten about the first definition. But at the moment, I'm not able to improve on what I said last time. There's a naive approach which doesn't work, and but probably some modification of it does. And which modification, I don't know. So let's state a goal for the next couple of weeks. The goal for the next couple of weeks is to prove the Poincare duality theorem for generalized homology and cohomology, which is basically stated in the same way it is stated for the ordinary for the ordinary homology and cohomology, let's briefly recall what the Poincare duality says. To simplify, let's assume that we have a manifold without boundary. And if we have a manifold which is orientable where R is a commutative ring, then we have the Poincare isomorphism between the homology and cohomology. Now we let's see if we can state this theorem for an arbitrary homology or cohomology theory. Well, firstly, we need to make sense of the left-hand side and the right-hand side. On the left, we have the cohomology of M. And the natural guess is to take a spectrum which represents a given cohomology theory. There could be several spectra which represent the same cohomology theory. Well, let's not worry about this for the moment. And let's recall we defined maps of spectra of degree R, which basically means the nth component goes to the n minus rth component, and we could take this as a definition. Very well. well, similarly, we can define homology as the homotypic groups of the smash spectrum. As if X is a space, and it is a space here, then the smash spectrum has a very simple definition. We just take X and smash it component-wise with all components of E. Well, so we can formally write the left-hand side and the right-hand side for an arbitrary spectrum. Now the question is how to interpret the fact that M is E-orientable. Well, let's see. Well, there are several ways to define orientability in the classical case. For example, there is a convenient definition which uses paths, and if all paths preserve orientation, then the manifold is orientable. Otherwise, it's not orientable. And there are several more. For example, the top homology of M may or may not be isomorphic to R, and if it is, then M is called orientable, and for every choice of isomorphism, we get a choice of a fundamental class, and so on. The definition, well, all those are equivalent. The definition which is the most convenient for our purposes is Viatom spaces. Well, let's denote the dimension of M by M. There's the Tom class. M is orientable if and only if there is a Tom class such that Well, recall that the tone class is a class of which lives in the relative homology of the total space of some bundle modulo the space of non-zero vectors, and the condition it has to satisfy is that the smash product by this class is an isomorphism between the homology of the total space and the relative homology of the total space mod non-zero vectors. Does this make sense? Very well. So let's see. Now this homology group can be rewritten as the homology, cohomology of the space of unit vectors mod. More precisely, we take all vectors of length less than or equal 1 with respect to some metric. It doesn't matter which one. And we collapse the subspace of all vectors which have length exactly 1. And now we're in business. We have here we have the relative homology of some space, which is something that makes sense for an arbiter E. Actually, let me think. Do I want to? Yes. So, yes, I want to put tildes everywhere, and if I want the non-reduced homology, I will just need to take the plus construction of I will just need to take x plus instead of x. So E without the tilde is E without the tilde is E with the tilde of x plus, where plus means we just add an extra point. So now we have a definition which generalizes to to arbitrary spectra, and we want to well, at least arbitrary ring spectra. And the conjecture, which sounds plausible, is that we have the same isomorphism for if M is E-orientable, then we have this we have basically the same isomorphism, and after we prove this conjecture, we will in particular prove this theorem. Okay, so this is the plan. Now the plan for basically the next 2 weeks or so, or maybe 3 weeks. Now, before we implement this plan, we need a little bit of abstract nonsense. So we need to define duality for symmetric monoidal categories. Okay, so there are symmetric monoidal categories. For example, the homotypic category of spectra is one of those, but the simplest example is vector spaces, and if you have a statement about symmetric monoidal categories and you don't know whether or not it's true, the first thing to do is to check whether it works for vector spaces. If it doesn't work, then there's your counterexample, and if it does work, then you have a fair idea of how you could try to prove it in general. Okay, so we have the monoidal unit, which we'll call S, YS, because the sphere spectrum and the wedge will denote the product because the smash product. Let's take two objects, x and y, and we will say that those two objects are dual if there exists an evaluation map x okay, let me check whether normally people denote there will be two maps, the evaluation map and the co-evaluation map. One is normally denoted epsilon, and the other one is denoted eta. Let's see which is which. Okay, okay. I'm looking at the the research project that one of my students wrote last year. So the student uses epsilon, so this must be correct. Okay, so we have the evaluation map X wedge Y to S, and the co-evaluation map Y smash X. No, what am S Y smash X, and these have to have the following properties. S, X, let's start with X. Let's say that, by the monoidal structure, X is isomorphic to X wedge S. Let's use this isomorphism. Then we apply the co-evaluation map. We get X wedge Y wedge X. Normally, I should okay. Let me put the parentheses once. After that, I will just drop those. Okay. Then I apply the associator map, and I basically transfer the parentheses one step to the left. And then I apply the evaluation map. And I get X wedge X, which is isomorphic to X by the monoidal structure, because S is the monoidal unit. So we have this map. And we require this map to be the identity. Okay, we have epsilon and we have eta. Well, similarly, we could take Y. And we could insert S on the left, because S is the monoidal unit. Then we apply the co-evaluation. Y wedge X wedge Y. Then we apply the associator Y wedge X wedge Y, and then we apply the evaluation. We end up in Y wedge S, and then we use the fact that S is the monoidal unit, and we end up in y again. So we start from y, we end up in y. And we require that the composite should be the identity. Well, let's see if this works for vector spaces. Vector spaces over a field K. So we sort of suspect that the spaces for which there's a sensible notion of duality are finite dimensional. And we so let's take x equal v2, y equal v for a finite dimensional space. Well, the evaluation map is clear. And it is the genuine evaluation. We can evaluate elements of V dual on V. Okay, so now we need a map from K to V tensor V dual. How do is there a preferred map from K to V tensor V dual? Well, let's see. So V tensor V dual is isomorphic to half VV, and we can indeed take x in K to x times the identity matrix and there we are. Now, in order for this to make sense, we need this isomorphism. If if V is infinite dimensional, then this isomorphism is no longer true. So the conclusion is we have this we have these two maps in the test example of vector spaces over a field, but only when the spaces are finite dimensional. If basically, as we will see as we will see today shortly, if we deal with infinite dimensional spaces, then it's no longer true that those are dualizable in this sense. Okay, so what next? Oh yes, we need to prove the following proposition. Suppose we have a symmetric monoidal category as before, and suppose we have x and y which are dual, and w which are arbitrary. Then I want to be able to transfer y to the right and make it x. So we start with the hump from C wedge y to W. We smash everything with x on the right. And then we apply the, well, I've messed up the order. Okay, so let me put an x here. So I will get an x here, and then I need to smash everything with y. So I take this smash everything with y, I get this. Then I applied the evaluation map on the last two factors, and I end up in Z W, sorry, wedge Y. Hold on. No. Sorry about this. Let me change everything into back to y, x, x, x. So the reason I'm confused is that the Helm functor is contravariant in the first argument. So I have the co-evaluation map from the monoidal unit to y tensor x, or y wedge x. So this map is the identity of Z. This map is induced by the identity of Z, wedge eta. And the co-evaluation map goes from nothing to y wedge x. So on the Helms we get there in the opposite direction. Does this make sense, Alexei? Jipping. Good. So we have this this map, and let me write another map. So I have this map. Now I want to go from this Helm set to this Helm set. What do I do? Well, it's more or less clear. We times everything with y. And then we use the so here I use the co-evaluation, and here I use the evaluation. So this is yes. This map is induced by the identity of W, wedge epsilon. So basically, we take a map from here and then compose it with the identity of W, wedge epsilon. Okay, so we have two maps. And my claim is that these maps are the inverses of each other. In particular, both of them are bijections. Well, let's see. Well, let's start with, let's compose this map with this one, and then the other composition will be similar. So let's call this 1. And let's denote the other one 2. Let's calculate the composition. First apply 2, then no. First apply 1, and then apply then 2. Okay, so we start with a map. Zy to W. We tensor it with X. Then we well, we precompose with Z goes to Y tensor X. And this is the first composition. Well, let's see what happens when we apply the other map, the one labeled 2. Well, firstly, we tensor everything with Y. So we basically here we tensor everything with y. Here I have something in the middle. Well, let me tensor it with y too. Okay, let me write it. Let me write it on the left. So we start with z tensor y goes to z tensor y tensor x tensor y goes to w tensor x tensor y, and then we post compose with the evaluation map, and we end up in W. So we start with an arrow z wedge y to W, and we end up with an arrow z wedge y to W. And the question is why are those arrows the same? And by the way, here I systematically ignore the fact that we have the brackets and the associators. If I didn't ignore that, then everyone would get lost, including myself. So, let's see. Okay, so the first map is the co-evaluation map, where x, wedge, y appear out of nowhere. And the second one is the evaluation map which collapses x, wedge, y. Well, I can do one of the two things. I can, starting from this place, I can wedge my given map from x wedge y to W with x wedge y, and then collapse x wedge y, or I can do it the other way around. I can first collapse x wedge y, and then apply my my given map. Okay, so let me see if I messed something up. Let's okay. I have this map. Okay, so let's go through the formulas again and see if there is if everything works. Okay, so x so here we okay, we start with x wedge y to w. We tensor it with x, compose with the evaluation. So the evaluation goes to no, we need to start here. Okay, okay, so the first error. The first error is the product of two things. We we go from the we go from Z to Z wedge Y wedge X by the co-evaluation, and then we smash it with the identity of Y. Well, the second arrow is self-explanatory. We take the identity of X smash Y and the given arrow from Y to W. And then we apply the evaluation. I want to check that this diagram commutes. Now, what does this arrow do? Well, this arrow just applies the evaluation on the last two factors. Okay, so the composite arrow is Y. So the composite arrow going from here to here and then here is first we apply the co-evaluation on the left of Y, tensored by the identity of Z. And then we apply the evaluation to the last two factors. By one of the identities in the definition of the dual objects, if we first insert Y wedge X on the left of Y, and then we collapse X wedge Y, we get the identity of Y. So on the Z component, nothing changes. We always use the identity. And on the Y component, we also get the identity because of the definition of dualizable objects. Okay, so this triangle commutes. What about the other one? Well, here we use the given map on the first two factors, the given map from Z wedge Y to W, and the identity of X wedge W, which we then collapse. But we may as well use the we may as well collapse the X wedge W first, and then apply the given map. Basically, we use the fact that smash product of two things can be decomposed into the composition of two commuting maps of the smashes of each of the things and the identity of the in the other place. So, we have shown, using one of the two defining identities for dualizing objects, that this composition is the identity. We start with something and we end up with the same thing. And my claim is, if we compose first 2 and 1, we also get the identity map, but this time we have to use the other half of the definition of dualizable objects. Are there any questions? Okay, so this is a technical proposition, but it will come in useful when we prove the Poincare duality, and it's completely general. Makes sense for arbitrary monoidal, symmetric monoidal categories. And there's a version of all this for not necessarily symmetric. Actually, we didn't use symmetry at all so far. But as we'll see, if the category is not just monoidal but symmetric monoidal, then the double dual of a dualizable object is the same as the object itself. And for non-symmetric categories, there's well, basically there are two notions of duality, and they're not the same. But it doesn't matter. We're not interested. We only want to know what happens for symmetric monoidal categories. Are there any questions? Okay, well, then let's have a break, and then we'll talk a little bit more about